Hey, welcome back to the channel, everybody. This is Kevin, and this week's video is a sample video from the CLCOR video training series that I'm currently developing. Specifically, we're going to talk about three things. Number one, we're going to do a calculation of how much bandwidth is going to be required for a phone to place a voice over IP phone call. Number two, we're going to take a look at a feature called regions. And a region can influence the codec selection. A codec is the coder-decoder. It can influence the codec selection within a site or between sites. And thirdly, we're going to take a look at a call admission control mechanism called locations, and even talk about enhanced locations. We'll take a look at the theory of all that in this video. And as always, if you enjoyed the video, it really does help the channel if you'll give me a like down below and subscribe so you don't miss any of our weekly content. Now join me in this fairly lengthy video where we're going to talk about bandwidth, regions, and locations. In this video, let's consider a design consideration. How does the bandwidth used by our audio calls and our video calls, how does that bandwidth impact an IP WAN interconnecting a couple of sites? Now, I focus on the IP WAN because we're typically not concerned much with the bandwidth of audio and video calls within a site. After all, we probably have our Ethernet switches interconnected with gig links or 10 gig links or even higher. But it's between those locations where we typically have less throughput that we want to pay attention to the bandwidth being consumed by our audio and video streams. First, let's consider audio. And the formula for calculating how much bandwidth total a voice call takes up is to take the total packet size and multiply that by the number of packets that we're sending per second. And we multiply that by 8 because the packet size is in bytes and we want a bandwidth in bits per second. So we multiply packets per second by 8 to convert bytes to bits. Now, how do we find the total packet size? Well, here's the formula for that. The total packet size, the name implies it's more than just the voice payload itself. We've got some header information to account for. We've got to add on the layer 2 header and the layer 3, layer 4 header. We typically combine those in the calculation. We add those headers on to the payload size. What about packets per second up in that top formula? How do we calculate that? Well, different codecs are going to have different bit rates, not including any overhead. We're going to take that codec bit rate and divide by 8. That's going to convert bits to bytes in this case. And we're going to divide that number of bytes per second that a codec is going to be using. We divide that by the voice payload size, and that tells us how many packets are we sending per second. Then we just plug and chug. We put in the total packet size and the packets per second. We put that into the voice call bandwidth formula. Now let's walk through these one at a time and see where we can find these values. First, consider the layer 2 header. Now here is a partial table. This is not comprehensive, but this gives you a good idea of common layer 2 overhead values. If we're using Ethernet, that's going to add on 14 bytes of header. And I know what you might be saying. You might say, no, Kevin, it's actually 18 bytes. Well, in the calculation, according to Cisco's latest design document, we don't count the checksum, which is 4 bytes. So yes, I agree. There's lots of literature out there that says the Ethernet header is 18 bytes, and it is if you include the checksum, but the most recent design document from Cisco says we don't include the checksum in this calculation. If we're doing point-to-point protocol, that's going to add 6 bytes. And I said this was only a partial table. If you want more information, let me point you to that design guide. It's called the SRND. That stands for the Solution Reference Network Designs. And Cisco is continually updating and coming out with new SRNDs as they release new versions of the unified communication software. But you can always go to cisco.com/go/SRND and just go to the most recent SRND. That's where these values came from, and you can see a more comprehensive table there. So we can use a table like that to get our layer 2 header. What about the combined layer 3 and layer 4 header? Well, we're doing voice over IP, so the layer 3 header is going to be the IP header, and it is 20 bytes in size. The layer 4 header, as we're streaming voice, we're going to be using UDP, a layer 4 protocol, which is encapsulating RTP, the real-time transport protocol, also a layer 4 protocol. That's right, we've got one layer 4 protocol, RTP, encapsulated inside of another layer 4 protocol, UDP. And UDP is going to take up 8 bytes, and RTP is going to take up 12 bytes. You add all those up, and you get a total layer 3, layer 4 combined header of 40 bytes. And this is if we don't try to do header compression on some types of links that we might have on the wide area network. For example, a point-to-point link. This would not work on Ethernet. But let's say we've got a point-to-point protocol link and we're trying to conserve some extra bandwidth. We can enable a feature called RTP header compression. Here's the logic. Imagine a router at each side of this link, and I'm sending frames as part of this voice call. And the router at the other end is looking at these frames coming in, and they say, these frames have a lot in common. They all have the same source and destination IP address. They all have the same source and destination UDP port number. They all have the same RTP payload type. This is redundant information we're sending in every single frame. So instead of doing that, let's just make a copy of this 40-byte header inside the routers at each end of the link, and then we can send a session identifier to say this is part of this voice call and this is part of this other voice call, and we'll allow the router at the other end to say, oh, you're part of this voice call? I've made a copy of your header with all the source and destination addresses and the RTP payload type. I'm going to put that back onto these packets as I receive them. As a result, instead of every packet having a 40-byte combined layer 3, layer 4 header, it has a 2-byte header. That's a huge bandwidth savings. And by the way, I say 2 bytes because that's what Cisco does by default, but you can enable UDP checksums to check for errors in your header. And if you do that, it goes from 2 bytes to 4 bytes. But in almost all cases, we assume that RTP header compression is going to take this 40-byte layer 3, layer 4 combined header and convert it into only 2 bytes. And at this point, we know how to get our layer 2 header size. We know our layer 3, layer 4 header size is probably going to be 40 bytes, or if we're doing RTP header compression, it's probably going to be 2 bytes. Next up, let's consider the voice payload size. And this is reference information. This is not something that we necessarily calculate. We look it up in something like the SRND. And the number of voice bytes being carried inside of a packet, that can vary based on our sampling rate. If we take a sample every 20 milliseconds, well, that's going to generate more frames per second than if we take a sample every 30 milliseconds, as an example. But usually, the default is going to be a 20 millisecond sampling rate, and at that sampling rate, we've got a voice payload of 160 bytes for both the G.711 codec, that's an uncompressed codec, and the G.722 codec, if we're using the 64K version of G.722. It has a lower rate variant as well, but we're assuming we're not doing compression there. Those have a voice payload of 160 bytes. If we use ILBC, that's the Internet Low Bitrate Codec, that's going to have a voice payload of 38 bytes. Again, that depends on the sampling rate. But if we have a sampling rate of 20 milliseconds, its voice payload is going to be 38 bytes. G.729, that's going to have an even smaller payload, only 20 bytes. Now, at this point, we've gone through every item in this total packet size formula. But something else we needed to calculate was the number of packets that we are sending per second. Here was the formula for that. We took the codec bit rate divided by 8 to convert bits to bytes, and we divided that by the voice payload size, which we just saw. Let's take a look at those same codecs again. If we're using G.711 or G.722, the 64K version of that, we already saw that it's going to have a voice payload of 160 bytes. Well, the bit rate is going to be 64 kilobits per second. And we would just take those two values of the bit rate and the voice payload size, and we would plug those into the packets per second formula. And typically, we're going to be sending 50 packets per second. Now that we know how to come up with all the different values for our formula, let's go through an example together. Here we're saying that the voice call bandwidth equals the total packet size multiplied by the packets per second times 8, because we're converting bytes to bits there. In this example, let's assume we're using the G.711 codec and we're doing it over Ethernet. Based on the tables I've shown you, we know that the total packet size is the layer 2 header for Ethernet, 14 bytes. Again, you could argue it's 18, but according to the latest SRND, it's 14 bytes. And we add that to the combined layer 3, layer 4 header, which is going to be 40 bytes. We're not able to do RTP header compression over Ethernet, so we know it's 40 bytes. And to that, we add the voice payload size. And for G.711, we saw, just looking it up in a table, that's 160 bytes. That means our grand total packet size is 214 bytes. How many packets are we sending per second? Well, that's going to be the codec bit rate of 64,000 bits per second for G.711, and we divide that bit rate by 8 to convert bits to bytes, and then we divide that value by 160. That's the voice payload size. Now we've got all the elements of our formula, and we're going to say that the voice call bandwidth is the total packet size of 214 bytes multiplied by 50, the number of packets per second, multiplied by 8, because we're converting those bytes to bits. And that's going to give us 85,600 bits per second. Or we could simply say 85.6 kilobits per second. And one time I created an Excel spreadsheet where I could just have columns and put all these different values in there and do some side-by-side comparisons. It's very easy to do that if you just want to use these formulas to set that up in some sort of a spreadsheet. But just as a reference for you, here is a table showing you for various codecs and various layer 2 media what sort of bandwidth demand we can expect. We just calculated that G.711 over Ethernet takes up 85.6 kilobits per second. We see that on this table. What about ILBC? That's going to save us some bandwidth, and it's going to take up 36.8 kilobits per second. If we're trying to save even more bandwidth, we could go down to G.729 over Ethernet. That's going to give us 29.6 kilobits per second. And each time we go down a little bit in bandwidth, we're typically sacrificing a little bit of voice quality. And ILBC is considered to be better quality than G.729. Let's take a look at what RTP header compression does. Let's go down to the bottom 2 rows. If we're using G.729 over a point-to-point protocol link, and we're not doing header compression, the PPP header is 6 bytes. The layer 3, layer 4 header, it's 40 bytes. Because we're not doing header compression, the voice payload size is only 20 bytes. And not including any overhead, G.729 has a codec bit rate of 8 kilobits per second. That's going to give us a total packet size of 66 bytes. We're sending 50 of those per second, and that comes out to a bandwidth demand of 26.4 kilobits per second. What happens if we turn on RTP header compression? Notice the bottom row. Instead of having a 40-byte combined layer 3, layer 4 header, it's only 2 bytes. We're not using a UDP checksum, so it's only 2 bytes. And if you do the math, it comes out to a bandwidth demand of only 11.2 kilobits per second. We can more than double our call carrying capacity in that instance by just doing RTP header compression. And on modern routers with modern Cisco IOS, that puts a negligible processor burden on our routers. That wasn't always the case, but it is now. And something we haven't mentioned is security. There is a variant of RTP, the real-time transport protocol, that will encrypt our voice traffic. If we want to do secure RTP, that's going to add 4 bytes to the voice payload size. Now, if you have this in an Excel spreadsheet, careful. If you have the packets per second value being calculated based on your voice payload size, it can throw your formula off. So just know that by default, you're almost always going to be using 50 packets per second. So you might just want to put that as a hard-coded value in your spreadsheet, because otherwise it could mess your result up. But let's say if we're doing G.711 over Ethernet, I would still say the packets per second is 50, but I would say my voice payload size was not 160, it would be 164. The extra 4 bytes because we're doing secure RTP. And that's a look at how we can calculate our voice or our audio bit rates. What about video? Well, video is a little bit more challenging to pin down because it can vary widely depending on what equipment we're using and how the video sampling is being done and what quality we're okay with. But let me give you just an example. And you can look at the documentation for your endpoint to get more information specific to you, or you could check out that SRND guide that I gave you the link to a moment ago. But just as one example, let's say that we're using Cisco Jabber. Here's a table that tells us how much bandwidth is going to be required for a specific resolution. For example, let's take a look at 720p resolution, high definition. That's a resolution of 1280 by 720. That's going to take up 1.3 megabits per second by our Cisco Jabber client. And that includes not just video, it also includes the audio portion as well. And specifically, we're saying we're using G.711 audio along with the video stream, and the audio and video combined for 720p resolution on Cisco Jabber, 1.3 megabits per second. And now that we have a better idea of how we can calculate how much bandwidth is being used by a voice call and or a video call, how can we control that? How do we prevent an oversubscription of that WAN link where we're trying to use too much bandwidth? Well, Cisco gives us a couple of tools we want to talk about. Regions and locations. First of all, consider regions. A region is going to influence the codec that's selected between a couple of regions. Now here I have two regions, one for HQ called HQ and one for Branch Office 1 called BR1. And what I can do, and we'll see this when we get into the configuration later on in the course, I could say within HQ, I'm not concerned about doing compression. I'm fine just using G.711 or the uncompressed version of G.722. I can say if a call is going from HQ to HQ, we're staying within the region, then I'll use G.722 or G.711. That's what shows up on the screen when you're selecting this. And we'll see that later again when we get into the configuration. Here's what's not obvious though. When I say, yeah, use G.722 or G.711, I'm not actually forcing one of those codecs to be used. I'm setting a bar, or a threshold, if you will. I'm saying whatever codec the endpoints negotiate, they are not allowed to negotiate a codec that will take up more bandwidth than these, which will be 64 kilobits per second, payload only. But maybe my endpoints wanted to negotiate ILBC or G.729. G.729 only takes up 8 kilobits per second. Well, that falls under the threshold of 64K that I've set by specifying G.722 or G.711. So yeah, if the endpoints wanted to use ILBC or G.729, they could definitely do that. Same thing within BR1. If I'm going from BR1 to another phone within BR1, I'm not concerned about compression. So I set that threshold at 64K by specifying those 64K codecs. However, where I'm most concerned about bandwidth usage is over that IP WAN. So let's say if I'm going between HQ and BR1, I'll set my threshold to the bitrate used by ILBC or G.728, and that's going to be assumed to be a value of 16 kilobits per second. Again, I'm not forcing the codec to be ILBC, I'm just setting that 16 kilobit per second threshold. Could I negotiate G.729 if that's what my endpoints preferred? Absolutely, because the G.729 bandwidth of 8 kilobits per second, that definitely falls under the threshold of 16K set by ILBC or G.728. Now what about video? When we specify video in a regions configuration, we're not saying here's the video codec, such as H.264. No, we're actually specifying a bandwidth amount. However, that amount that we put in for the video bandwidth, that includes not just the video, it also includes the audio stream. However, it doesn't accommodate for any overhead. So let's say the video bandwidth was set to 384 kilobits per second. Well, if you're using G.711 as your audio codec for that video stream, we know that G.711 takes up 64 kilobits per second. So we would subtract 64K from 384K, giving us a video bandwidth of 320K. But we have not accounted for overhead. And one design best practice that some people use is to add 20% to whatever bandwidth value you come up with to accommodate for that overhead. And when you're setting up the video bandwidth, you're going to have two different settings. And we'll see this when we get into the configuration later in the course, but there's going to be one setting for video calls. That might be for Cisco Jabber or for your 8865 Cisco IP phones as a couple of examples. But there's another setting for immersive video calls. When you see immersive video calls, think telepresence. Maybe we want to grant some extra bandwidth to those telepresence rooms. So regions, that's going to help us preserve our IP WAN bandwidth by influencing the codec selection between our sites. However, we don't want to oversubscribe the IP WAN, even if we do all of our best effort to minimize the bandwidth usage. If we place too many simultaneous calls over the IP WAN, it's not just the last call, the call that broke the camel's back. It's not just that call that has poor voice quality. It's everybody, because everybody is fighting it out for too little bandwidth. So let's take a look at a feature called CAC, Call Admission Control, or CAC. And there is a CAC feature built into Cisco Unified Communications Manager called Locations. And Locations has been around for a while, and we're going to take a look first of all at traditional locations, and then we'll take a look at an enhanced version of locations. But by default, we have a location that's named Hub None. And let's say that's the location to which we assign our headquarters site. It belongs to Hub None. And Hub None should give you a sense that this was designed with the assumption we're using a hub and spoke topology. Let's say I have a location in Louisville named Louisville, and I have a location in Lexington named Lexington. And we can go in and configure these locations as having 512K going to Louisville or 128K going to Lexington. In a case like this, traditional locations work great. We can start deducting bandwidth from this total every time we place a call. And when we run out of bandwidth, we say, nope, sorry, you're going to be rejected. And we might have some backup path selected. We could set up something called AAR, automated alternate routing, which might send the call out over the PSTN to get over to Louisville or Lexington. But here's where traditional locations start to break down a bit, where we're not in a purely hub and spoke environment. Let's say I have an additional link going between Louisville and Lexington, and that link has a bandwidth of 256 kilobits per second. Now we can look at this and say, oh, it would be more efficient to go from the HQ site down to Louisville and then over that 256K link over to Lexington. But traditional locations will not see that. It will have no knowledge of that 256K link because it's not coming into the Hub None location. So if we try to go from HQ to Lexington, we're going to take that direct path. Here's another instance where we might have a breakdown with traditional locations, and that's when a location is a transit location. Let's say, for example, that I've got a link to Orlando, and through the Orlando location, I get to the Tampa location. And if I go into my locations configuration and say, I've got a 128K link to Tampa, because that's the speed between Tampa and Orlando, and I've got a 256K link between the Hub None location and Orlando. Locations would not view that correctly. Locations would think that we could be using 128K going to Tampa while simultaneously using 256K going to Orlando. That's not going to work because that 128K available to Tampa, that comes over the Orlando link. Because of situations like these, traditional locations can break down if we have anything other than a hub and spoke topology. So how do we address this? Well, the great news is there's now something called enhanced locations. With enhanced locations, it's a lot like OSPF. With OSPF, we assign a cost to each link based on bandwidth, and we do a calculation to determine the shortest path in terms of cost to get from point A to point B. Well, with enhanced locations, we're going to specify weights based on bandwidth. And here I'm assigning a weight of 40 to that 128K link between Orlando and Tampa, and a lower weight, a more attractive weight of 20 between Hub None and Orlando. And I won't read the rest out, but you see the higher the bandwidth, the lower the weight. Now, based on this, if I wanted to go from the Hub None location to Lexington, I would look at the weight. I would no longer take that direct path over the 128K link that has a weight of 40. I would instead say, I'm going to go down to Louisville. That's going to give me a weight of 10, and then go from Louisville over to Lexington. That would add on the weight of 20. So we would have 10 plus 20. That's a grand total weight of 30 if I go from Hub None to Louisville to Lexington. That's less than the weight of 40 if I go directly to Lexington. So that's the path I'm going to take, from HQ's Hub None location to Louisville to Lexington, and that's called the effective path. And you might wonder, when we're putting in these bandwidth amounts into our locations configuration, which we'll see later on in the course, are we including the overhead as part of that bandwidth or not? Well, it's interesting. We're going to consider some overhead, but we're not considering layer 2 overhead. Well, here's a table. And again, there are design documents that you can check out at Cisco's website. But this table shows us the link bandwidth we would put into a locations configuration for something like G.711, 80 kilobits per second. We're including layer 3 and layer 4 overhead there, but we're not including layer 2 overhead. For one reason, we're not sure what that overhead would be. We don't know what the layer 2 media is. And for video calls, if you have a 128K video call, that's the bandwidth you put in. We're not adding any header on to that video stream, and that includes both the video and the audio. So that's enhanced locations, and it does a great job of call admission control. One slight potential challenge we have, though, in order for this to work, all of the servers in the cluster that are going to be placing these calls, they need to have a service running called the Location Bandwidth Manager, the LBM service. And in order for this LBM service to work by default, we have to have a full mesh of connections. Every server running the LBM service has to talk to every other server running the LBM service. And with 3 servers, it's not a big deal. But if we have a few more servers, it might start to create some extra overhead that we just don't need. So here's an option. Let's say for that Communications Manager server on the right, we're going to stop running the LBM service. And we're going to take the remaining 2 Communication Manager servers. We'll continue to run the LBM service on them, but we're going to say that they belong to this LBM group. And instead of that server on the right having a full mesh of connectivity to all the other servers, it just has to have a single connection over to the LBM group. Again, not a big deal with only 3 Communication Manager servers, but you can see how this would really help with scalability within a cluster. And speaking of clusters, what we've been considering is within a cluster, what if we're trying to do locations-based CAC between clusters? Well, we can continue to use enhanced locations. Check this out. Let's say we've got 2 clusters, cluster A, cluster B, and we've got our Communication Manager servers running that LBM service. But in addition to those servers belonging to an LBM group, we can have 1 or more servers belonging to an LBM hub group. Now, the function of a server in an LBM hub group is to talk to other servers in LBM hub groups. So we're going to have the server in the LBM hub group for cluster A form a SIP trunk with the LBM hub group in cluster B. And we can educate our locations configuration about that SIP trunk interconnecting our clusters. So to wrap up this video, we've taken a look at the bandwidth required for an audio call, the bandwidth required for a video call, and how we can preserve WAN bandwidth between a couple of sites by influencing the codec selection using regions, and how we can prevent oversubscribing one of those links by using either traditional locations, or if we have something other than a pure hub and spoke topology, how we can perform call admission control using enhanced locations, both within a cluster and between clusters.